In the last video, we followed Andrej's path and built up a lookup table which provided us the probability of predicting any character given a certain character in our datasets. At first, we built this table by simply counting the occurrence of all possible character pairs in the datasets. We then moved forward to take the gradient descent approach to reach the optimized lookup table. This approach is more scalable and more dynamic, and with the approach, we started to get a sense of how modern neural networks training is performed. In this video, we will follow Andrej's path again and build a smaller model to further optimize the loss. We will introduce three key concepts in this video. They are character embedding, multi-layer perceptron, hyperparameter tuning. We'll go through these key three concepts and pick Andrej's brain on how he tunes the training process and hyperparameters to get the optimized results. This video is essentially my notes on Andrej Karpathy's original video. His original video contains a lot of warm teaching on technical details and nuances on PyTorch. While these details are neglected in my video, I highly recommend that you watch his original video to get a comprehensive understanding of the fundamental techniques. A smarter model should be able to take more useful information from the datasets. Previously, our Bigram model only used one character to predict the next character. This does not grasp all possible patterns in a name. A better way is to use more than one character as an input. For example, we use 3 characters as an input. We call the group of 3 characters context. The output will stay the same. We then split our data into 3 portions: training, validation, and testing. By doing so, we can ensure that our model isn't just memorizing the patterns in training data, but is capable of generalizing its learned patterns to new unseen data. The model we used was introduced in the Bigram 2003 paper. In this paper, the author discussed the limitation of n-gram, or bigram in our case. First of all, it's not taking into account context length larger than 1 or 2 words. With increasing length of input sequence, these methods will face the so-called curse of dimensionality. Second of all, it's not taking into account the similarity between words. For example, this sentence, "The cat is walking in bedroom," is very similar to "a dog was running in a room," simply because dog and cat, walking and running, room and bedroom have similar semantic and grammatical rules. The probability function of a word sequence was then built in terms of the feature vectors. In the training process, the word feature vectors and the probability function are learned simultaneously. We will follow this rule, except that in our case, we assign each character in the name a feature vector, and then each feature vector has 2 dimensions. Here, we use a 2D embedding matrix with shape 27 by 2. It takes an 1-hot encoded input and outputs a 2D feature vector. In the last video, we demonstrated that a 1-hot encoding is essentially row retrieval. We will simply retrieve the feature vector for each row by class index. To construct the embedded vector for 3 characters, simply concatenate their feature vectors into one flattened vector. Such a feature vector contains 6 numbers, and this will be our input layer. Let's take a look at the model architecture. As we can see, the architecture has one hidden layer. To get to this layer, the input layer is multiplied by the weight matrix to produce the pre-activated layer. Then a 10H activation function is applied to this pre-activated layer to produce the hidden layer. The hidden layer is then multiplied by a second set of weights and bias to produce the output layer. Remember, our model output is supposed to be the probability of a predicted next character. So we do need to apply a softmax function to turn logits into probabilities, just like what we did in the last video. The loss function is the same negative log likelihood function that we used in our last video. In fact, a softmax function followed by a negative log likelihood function is equivalent to applying a cross-entropy loss function. You can check more details about cross-entropy loss function in PyTorch documentation. From now on, we will wrap them up and use cross-entropy loss function instead. Now let's move on to setting up the training loop. First of all, let's initialize all parameters needed in this model and turn on their gradient for backpropagation. In practice, we don't want to hard-code any magic numbers into the training loop. Here we define two hyperparameters, the dimension of the embedding space and the size of the hidden layer. They are used to control the size of our model. In the training session, we define two hyperparameters. One is learning rate, a variable to control how fast the gradient descent happens. This variable cannot be too large or too small. The other one is batch size, which controls the amount of data fed into the model at each iteration. Instead of feeding all the data at once, we feed a small batch of data points at each iteration. This can make the training more efficient, though the downsides of this is that we will introduce more noises to the loss. These four variables are hyperparameters. Unlike weights and bias, they are fixed for each training session, but they also need to be optimized to find the best performance. This process is called hyperparameter tuning. And I think the most valuable part of the video is hyperparameter tuning. Andrej spent quite a bit of time showing how he tunes hyperparameter by hand. In production, this process is always set up automatically, but it is worthwhile to go through this process by hand. By doing so, you can build an intuition of how things work on a fundamental level. The first hyperparameter tuning is learning rate. While you can make some educated guesses till you find the best learning rate, it is recommended to do so in a more systematic way. The best practice here, as introduced by Andrej, is to set the lower limit and higher limit of the possible learning rate and span the entire range in one training loop. For example, I found 0.001 and 1 are the limits of the learning rate. Beyond the limit, it doesn't help with the loss anymore. Now you change the learning rate from low to high during the training and plot out the loss against the learning rate. The lowest loss indicates the proper choice of learning rate. How do you know when you are underfitting or overfitting to your training data? This is where your validation data comes to play. The thumb of the rule is when training loss is approximately equal or slightly higher than validation loss, there is still room for the model to learn from the data. That means our model is not powerful enough to generalize the patterns. One way is to increase the model size. In our case, to increase the size of hidden layer or the dimension of the embedding space. On the other hand, when training loss is slightly lower than the validation loss, this shows that the model starts to overfit to the training data sets, and it is time to stop the training. At last, let's take a look at the trained 2D embedding space. It's very interesting to see that all the vowels are grouped together. That makes sense because vowels play similar roles in a name. Some characters are far away from all other characters. That means their roles in a name is unique or rare. Q are rarely used in a name, and dot only denotes the beginning of the ending of a name. As you can see, the model starts to learn the internal relationships between characters in a name, and the names sampled from the trained model starts to make more sense compared with the names we sampled in our last video, and some of them sound like real names. There are still room for improvements though. In the next video, we'll explore more complex structures and more engineering techniques toward building more powerful model.